Ну хорошо, значит, опять нужно повторить, что было до каникул, то есть, вернее, до сессии. У Борхеса есть рассказ про человека, который вспоминал свою жизнь очень подробно, типа как Марсель Пруст, настолько подробно, что у него как бы, воспоминание одного дня занимало как раз один день. И вот мы примерно в такой ситуации находимся. Значит, у нас были такие премногочлены Литлвуда, сумма по перестановкам, да, и потом мы определяли настоящие многочлены Литлвуда как r лямбда делить на v лямбда. Кроме того, также было верно, что это сумма по классам смежности, по стабилизатору лямбды похожих выражений. Да, значит, v лямбда было произведением в m итах от t, и лямбда было и в степени mi, и начиналось от нуля, но длина лямбда была, включая 0, была ровно n. Да.
Получается, сигма лямбда — это перестановки, сохраняющие
S лямбда, да, это стабилизатор лямбда, да, совершенно верно. Угу. Да, и в какой-нибудь mt от t было коаналогом факториала. И это еще связано с другим коаналогом, который у нас раньше был в упражнениях, который нам сейчас пригодится. Значит, кроме того, было известно, что для разбиения на единички соответствующий многочлен Холла — это просто элементарный симметрический многочлен. Кроме того, мы определили маленькие QR многочлены как многочлены Холла, чуть-чуть отнормированные, связанные, наоборот, со строчным разбиением. После этого мы определили Q альфа для произвольной композиции, неважно, что упорядоченной, и даже не обязательно, что композиции, для последовательных целых чисел, как произведение Q альфа-итах, и Q альфа-ита равно нулю, если альфа-ита отрицательно, а наоборот Q нулевое равно единице. Что еще? Еще мы определили большие перенормированные или двойственные многочлены Литлвуда как b лямбда на p лямбда, а b лямбда это аналог этого v лямбда, то есть произведение фи m и t от лямбда от t. Окей. И еще мы определили понятие итой, так сказать, частной производной. Это когда ита переменная обращается в нуль. И, господи, значит, доказали в прошлый раз утверждение, что q лямбда это сумма прошу прощения, x ита в степени лямбда первая. Да. Что?
Сколько букв f на вход принимает?
N. Сейчас, прошу прощения. Скорее она принимает n-1 букву. Ну да, если угодно, x ита здесь можно вычеркнуть.
Грубо говоря, у нас f ита это мы просто зануляем итую.
Ну да, зануляем итую переменную. Поэтому она зависит от остальных n-1 переменной. Окей?
Хорошо.
Значит, у ита q лямбда с волной ита, где...
То есть ита переменная на вход все равно подается, но от нее ничего не зависит.
Ну, можно так считать, да. Значит, лямбда с волной — это когда мы выбросили первую строчку, а у ита это 1 минус t умножить на произведение по всем, кроме иты, x ита минус t, x житая, x ита минус x житая. Окей, это вроде бы то, что было в прошлый раз. И, наконец, я сформулировал утверждение 4, которое мы сейчас будем доказывать, что q лямбда получается применением повышающих операторов к маленькому q лямбда, где повышающий оператор действует просто номера. Q лямбда 1 и так далее. Потом лямбда g увеличивается на единичку, лямбда кт уменьшается на единичку, ну какой-то лямбда лт. So let's prove it. Just by induction in the length of lambda. So when L equals 1, it is just Q R equals QR, and that's fine. Now, let us have at least two rows, and assume we proved the claim for lambda tilde, which is, pardon me?
Можете еще раз повторить утверждение?
This one?
1 минус r ЖК.
Yes.
R ЖК это...
It's some formal thing. Well, from Q lambda, when you apply this to Q lambda, you obtain some other Q lambda. This is lower index. Q with this lower index.
Не получается прямую формулу.
Yeah, if we obtain something negative from this operation, then by definition, this is 0. Just because Q is defined as product of Q for numbers and Q for negative number is 0. Okay. So assume that we proved for lambda from which we removed the first row. Well, last time we proved also some lemma 2, which I didn't recall, but it says that the sum of the generating function of Q R with ith variable set 0 is 1 minus xiy over 1 minus t xiy, the sum of qr y to the r. Well, I mean, we had such a generating function, and it was equal to infinite product like this. But then if we remove one variable, we remove one factor from this infinite product. Okay, so there's just this lemma of the previous time. Yes?
Не понимаю, лямбда с волной, как оно с нуля может начинаться? Это же какое-то разделение, нет?
But we
Или мы просто там не должен быть ноль, должно быть ничего?
okay, maybe nothing.
Лямбда с волной там, может, лямбда 2, лямбда 3 дали?
Pardon me?
В лямбда с волной, кажется, там лямбда 2, лямбда 3 должно быть.
Yes. We just remove the first row, and now we can compare the coefficients of y to the power r. We get that Q R with ith variable removed is equal to 1 minus xi e over 1 minus t xi e applied to QR, where E is a sort of raising operator, or maybe rather lowering operator. EQM is defined as QM minus 1 for any M. Okay. And then we see that Qi lambda tilde is just the product from k equals 2 to L, the length 1 minus x I ek over 1 minus t x I ek q lambda tilde, where ek applied to q alpha is q alpha 1 and so on, and then alpha k minus 1, sorry, alpha k minus 1, this way, and so on and so forth. Okay, now consider the sum of xi to lambda 1 ui q lambda tilde with ith variable removed. And this is the sum over xi lambda 1 ui, the product from k equals 2 to L, 1 minus xi ek over 1 minus t xi ek q lambda tilde. Ui is here. So we know that sorry, just one moment. Yes. Yeah. So we know just from this very first formula for p lambda, and where lambda is one row. When we defined small qr, it was pp for one row partition. So we know that qr is equal to 1 minus t times the sum of xi to the r, the product xi minus t xj over xi minus xj. We know this, and this means that q lambda 1, in particular, just for r equals lambda 1, is the sum of xi to lambda 1 ui. And hence the sum of xi lambda 1 ui q lambda tilde with ith variable removed is the product of 1 minus the raising operator 1k 1 minus t r1k q lambda. Okay, and now from this formula, which we proved last time, we conclude that maybe end the induction assumption. conclude that q lambda equals the sum of xi to lambda 1 ui q lambda tilde with I variable removed, and this is equal to the sum of xi to lambda 1 ui, the product over j less than k less than length of lambda 1 minus r jk over 1 minus t rjk q lambda tilde with I variable removed. And now we compare with the with this. And get what we want. Okay. So if we just expand this as a geometric progression, we get the product over j less than k, 1 plus t minus 1 r jk plus t squared minus t r jk squared plus so on applied to q lambda. And now this is needed for the following corollary, that q lambda form a basis of lambda tensor rational functions in T over rational functions in T. And the transition matrix from small q to big Q is strictly lower triangular. And this is proved immediately because R jk is a raising operator. Which means that R whatever lambda is bigger than lambda, and hence big Q lambda capital Q is the combination of with certain coefficients a lambda mu of T small q mu, where a lambda mu of T is an integral polynomial of T, and a lambda mu of t is 0 unless lambda is dominated by mu, and a lambda lambda of t is just 1. Okay.
Почему можем утверждать, что r лямбда больше равно, чем лямбда?
Just by definition. Yeah, here it is. Yeah, we just take one box and place it higher. It's just the definition of the dominance order. This is the
У нас там до момента, пока... То есть, грубо говоря, из-за того, что у нас лямбда житы плюс 1 больше, чем лямбда житы, у нас из-за этого как раз и будет лямбда больше равно, чем лямбда.
yeah, just the dominance order, by definition, is generated by such elementary order relations. Well, maybe it is literally generated in the case when k is j plus 1. Then these are well, minimal adjacencies.
Сейчас, еще раз, у нас лямбда должно помещаться внутрь лямбда, так?
No, it looks like
Сейчас, возможно, я просто не... у нас, все, я понял, у нас в каждой новой строке, сейчас, до каждой новой строки у нас было больше равно клеток, так?
something like this, yeah. So we would take a box, say here, and place it, say there. So the number of boxes is the same. Otherwise, they're incomparable of this in the dominance order. But okay, and now we can prove that the Littlewood polynomials are equal to the whole polynomials. So we define the structure constants f lambda mu nu of t, some integral polynomials. So when we multiply p mu and p nu, we get sum over lambda of these structure constants times the whole Littlewood base. Then we know that the constant terms of these polynomials are just the Littlewood-Richardson structure constants. Yes. Of lambda in the basis, in the Schur basis. We know this since we know already that p lambda at t equals 0 equals s lambda. And now the next case we are going to prove is that some specific structure constants when nu is just one column partition, is the product of Gaussian binomial coefficients. Sorry. Okay. Well, in your home assignment, there was an easy exercise that this is essentially the same as similar structure constants for the whole algebra. And that's enough. Well, I mean, we need to prove this, but if we prove this, everything will follow, because these guys are generators. The little polynomials for those, they are just, in fact, elementary functions, and they generate. They don't form a basis, but they form a generator set of lambda. So if we know how to multiply with generators, it's enough. So as I will say a few more words about this later, let's prove this claim first, but at least morally it's enough. But maybe you have to distribute tangerines meanwhile. So we found the structure constants like this for the whole algebra by counting, just by definition, by counting certain flags in all modules. And here we will count the multiplication, because we know that the whole little wood polynomials for column partitions are just elementary symmetric functions. Yes?
Почему правая часть от m не зависит? Или там m должно быть таким, чтобы вес лямбда какой-нибудь нужен был?
Well, if you, it depends on mu and lambda, right? The right-hand side. But certainly m can be reconstructed from mu and lambda, because the total size of lambda is the sum of total size of mu and m, right? So m is implicitly contained on the right-hand side, just as the difference of total size of lambda and mu.
Сейчас вот это хорошо, еще более вопрос. m, ну, вес разбиения – это как бы степень однородности по x, да?
Right.
А по t однородность есть какая-то?
No.
Степень она вот по x.
Yes, certainly, yes. So the sum of these guys is m over all I. Okay, so we assume there are n variables, x1 and so on, xn, but n is big enough, so it's bigger than length of mu plus m. And we know that P column partition is just EM, elementary symmetric. So set k equals mu1 and split the set of variables into groups, well, subsets, capital X 0 and so on, capital X k, so they may be empty. Such that well, mu equals this, and the cardinality of xi is mi, so that small variable xj lies in the subset xi if mu j equals I. Now let ER of xi be the elementary symmetric polynomial of the group xi. Then the generating function of elementary symmetric polynomials in all the variables splits into product inside groups. And so elementary symmetric polynomial in all variables splits into the sum over something. Elementary symmetric polynomials in groups R0 of x0 and so on, Rk of x, capital Xk. So the summation over all vectors R such that Ri is at most mi, otherwise the elementary symmetric polynomial will vanish, but the sum of all Ri's is m. Then to a vector R, we associate a partition lambda as follows. The transposed partition lambda I transposed is mu I transposed plus Ri minus 1. And then I will draw a picture in a moment. Then the skew-Young diagram, the complement in lambda to mu, is a vertical M strip, meaning that in each row there is at most one box of this skew diagram, and all such lambda are obtained. Okay, so now let me draw a picture. Oh, well, okay. And so on. So this is mu, which is smaller. This is mu. And now we can attach a vertical strip. So we can attach something here, but well, for example, this. Yeah, but and here, for example, this, but not lower, certainly. And here, and here. So this will be lambda. Okay, and well, this will be our R1, R2, R3, R4. Okay? Yes.
То есть нам, получается, в лямбда минус мю допускается такой пропуск.
Yes, certainly, yes. But this is M1, or maybe I sorry. No, I screwed up with numbering. So this is not M1. This is M what? This is no. This is this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's rather M14, I think. Right? M14 equals 2. And this is M12. Am I right? M10. And this is M6. No, M5. No, I am drawing not here. It's M11. It's M9. And M5.
M12?
Yes, after M14 it will be M12.
M is for mu, right? M is for mu. And mu is smaller. So mu is 14 to 2, and then 11 to 3, and then 9 to 4, and then 5 to 6, right? Pardon me? Pardon me? Right. Thank you. White and yellow is hard to distinguish. Okay. Is it? No, it's even harder now, right?
It's already late. Now everything is clear.
Now everything's clear. Okay. Fine. But now this it's not R1. It's R what? It's R.
It's R14. We have Ri less or equal than Mi.
Ri less equal to Mi. Right. So R14. But other R's are just vanish, right? They just vanish. R11, R9, R5. And other R's are 0, right? I think now it's right. No? Misha, you don't agree? Okay. So there is a bijection between such vectors and such lambdas. And I mean, those lambdas are exactly the ones that will appear after multiplication by 1 to m. So, okay. Now we know that E Ri over xi is the column Littlewood polynomial over ith group. And from this, we get that Em, because we know that Em is given by such formula. It is the sum of certain quantities. I will explain what I mean by this in a moment. So summation over all lambda such that the skew diagram is an M vertical strip. So here phi lambda mu is the sum over all permutations stabilizing mu. And C lambda mu is the product of V Ri of T V Mi minus Ri of T. So here I just use the expression for P, the very, very first one. By P, but maybe not lambda, something, I don't know, nu equals, maybe not theta, is R theta over V theta. No, just over the product of, because I replace each ERI here, I view as the Littlewood polynomial PRI. Okay? But this, well, I don't know, ERI is PRI of the variables in the group I. And this is X, I don't know, something 1 and so on, something MI. And RI is smaller than MI. It's subset of MI.
Хорошо, но там тогда, где произведение B меньше G, будет много лишних множителей, да?
But well, this is just definition of PP lambda. Okay. Now, unfortunately, I need just a bit more space. So let's multiply both sides of this equality by P mu over x1 and so on, xn t in the form there. Well, okay. And now what happens? You see here we have some product over right cosets. And here we have some product over this stabilizing subgroup. So when we multiply, we get not a product, it was sum. The sum over right cosets and the sum over the stabilizing group. And when I multiply them, we get the sum over Sn, over the whole symmetric group. P mu times em in the left-hand side. In the right-hand side, we get the sum over lambda c lambda mu of T inverse did I have? Yeah, I had. R lambda, and that's it. So this means that the coefficient of P lambda in P mu times Em equals V lambda of T C lambda mu. Oh, sorry, it's inverse here of T inverse, and that's just what we wanted. The product, just this product. Okay. So this is proved, and maybe let me erase the beginning of the proof. And deduce the equality of whole polynomials and Littlewood polynomials. So maybe corollary of this claim that the structure constants in the whole algebra are equal to the structure constants of Littlewood polynomials, slightly renormalized. So it's q to the power n of lambda minus n of mu minus n of 1 to the r f lambda mu 1 to the r of q inverse. Well, where? Okay, and now the long-awaited theorem is that well, a linear map psi from the whole algebra to lambda q that takes a basis element u lambda to q negative n of lambda p lambda of x t equals q inverse. Here, But you see, I specialize T to just a rational number Q inverse. So, well, okay. So this is an isomorphism of algebras. And I already argued that it's more or less clear by now, because we know that the structure constants for generators, U, well, lambda is a column, are the same. They match, but maybe let me spell out a formal proof. So we know that on the generators, U1 to the R, we have psi of U1 to the R is equal to Q negative R minus 1 over 2 ER. And extend this to a homomorphism, because we know its value on generators. Psi prime, then we want to prove that psi equals psi prime. And then we do this by induction in lambda. So let mu be lambda with the last column removed. And let m be the height of this last column. Then the structure constant of this particular triple, when we just remove the last column, yeah, like over there, R14, is just 1. Well, from the point of view of the whole algebra, it is just the circle, and it's unique. And from the point of view of Littlewood formula, again, there will be ones everywhere. So it will be something. Choose. I don't know. A choose A, and A choose 0 in the end. In this product, it will be A choose A and A choose 0. Okay, so this is 1, and in fact, when we multiply mu and 1 to the m, then lambda, this lambda will be the maximal thing that could possibly appear. So it's 0 unless nu contains mu, and mu without mu is an m vertical strip. And then nu is necessarily at most lambda. And hence we know that u mu times u1 to the m is u lambda, because this structure constant was 1, plus certain sum with certain coefficients, but all the entries in this sum are strictly less than lambda. And we also know the same thing for Littlewood polynomials. P mu times p1 to the m is equal to p lambda plus the sum, just the same sum, f nu mu 1 to the r p nu. Well, p nu of x and q inverse. So apply our induction assumption to the equality in the whole algebra. And get that psi prime over u nu is equal to q negative n of nu. P nu for any nu less than lambda, and hence in this sum everything matches, all the junk, so to say, matches this junk, and the left-hand side also match. So the interesting part, p lambda matches u lambda. Oh, sorry, no, not quite. It's q to negative n of lambda, p lambda of x q inverse. That's it. And it's a perfect timing. So we're done for today. Next time, or maybe next time, we will study some orthogonality relations for whole Littlewood polynomials. And next Tuesday, we will finish with whole Littlewood polynomials and start McDonald polynomials.